This is active filter design, lecture 17. In the last class, we saw how one might design an active filter with only voltage controlled current sources and capacitors this is the band pass node and this is the low pass node, right. This is the input. Now, we also concluded that since we now know how to make a second order section, in other words a building block which will give us a second order denominator and a numerator which is some constant k, we can in principle cascade such building blocks in order to realize any arbitrary transfer function where the numerator is a constant, correct. Then one natural question that comes about is there a smart way of ordering the second order sections, or is it that any arbitrary order is fine? Okay, that's a natural question that arises. If we study and then we conclude that any arbitrary order is fine, that's good. If some orders are better than others, I mean some order of cascading is better than others, then obviously we must use that kind of order, right. So that question has to be addressed. Before we are able to address that, we need to learn a few definitions and issues associated with such filters. It is understood that these voltage controlled current sources will all be realized using some circuit arrangement of various transistors. Okay. So all these are going to be realized using transistors which are which can be biased in such a manner to behave like incremental voltage controlled current sources. And one thing that's also understood is that these transconductors have additional terminals which are the supplies. Okay. You just can't have a voltage controlled current source floating in thin air, right. So there are supplies, which basically means that you can assume that the filter is operating between some pre-assigned supply voltage, okay, one being ground and the other being some supply voltage, like all active circuits. And therefore, one key point that one must bear in mind is as the difference between an ideal transconductor for an ideal transconductor, regardless of the magnitude of V, the I will always be the slope will be GM, okay, for arbitrary V. If I put a million volts, it will be GM times a million volts will be the current output, okay. But obviously no real transconductor can behave like that, okay. When you have a real transconductor, what do you expect to happen? What happens is that simplistically speaking, one can expect a finite range of voltage beyond which the current is no longer related linearly to the voltage. Okay. The exact nature of this dependence will depend on the way transistors are arranged inside the transconductor in order to realize this functionality. But at this point, one should be able to accept without too much protest that, yeah, sure, while I can't at this point predict how exactly this curve looks like, I must definitely expect a range beyond which the voltage cannot be, the current cannot be linearly related to the voltage. To make the most simplistic of assumptions, I will assume that the GM, the I versus V characteristic has a constant slope in this region and zero slope elsewhere. Okay. In reality, of course, when you take a real transistor level design, the real thing may be perhaps something like, that no real circuit will exhibit such strong kinks. So a real thing is probably something like that, but we don't need to worry about that at this point because we have not seen any circuit so far. The only thing I wish to bring to your attention is the fact that the transconductor has a definite linear range. Okay. So in other words, within the linear range, let's say the input to the transconductor was a function of time, and this was the input voltage to the transconductor, and this was the linear range. Please assume that this is this fellow here is a sinusoid. Okay. If this is the case, what comment can you make about the shape of the current waveform coming out? It's also a sinusoid at the same frequency and the same phase and all this other stuff. Now, if the sinusoid amplitude got bigger, for example, like this, okay, and this was the linear range. What would be the output current waveform? It will be quite nice around here, then get clipped, and then do this. Similarly, do this, get clipped, and then do this. Okay, this is I versus T, this is V versus T. So this represents a situation where the input exceeds the linear range. So what observation can you make at the output, or rather what observation can you make regarding the current waveform? It is clipped. Okay. In other words, if the input tone is a pure sinusoid, what will you see at the, you will see in general a whole bunch of harmonics, where the level of harmonics is dependent on how much the input exceeds the linear range. Okay. So in other words, if the input exceeds the linear range, the transconductor distorts, or which is equivalent to saying that I has components at harmonics of the sinusoidal input. So, is this do you think this is a desirable attribute or it is not desirable? Why is this not desirable?
Because we are designing a filter.
Yeah, if you are designing a filter, so what?
Because at certain level it may happen that the filtering work has been done. After that, if something this transconductor is doing, this will again generate.
Yeah. Okay. So one way of thinking about it is if you had, for example, a filter and you wanted to get rid of one sign. Let's say the input signal was 2 tones, and you wanted to get rid of one while letting the other through. Now, if the transconductors start to distort because the input at some point exceeds the linear range, then the filter is adding its own set of tones, okay, harmonics of one frequency or the other, or a combination of the sums of the harmonics of these input tones. Therefore, distortion is something that you do not want. Okay. So, if you do not want distortion, what is the moral of the story? You should make sure that at no point in time the input to the transconductor should exceed the linear range. Okay. Now, the linear range in our case is very cleanly defined, right? The what do you call the I versus V was assumed to be a straight line for some time, for some range, and then another straight line, but with 0 slope beyond that range. Okay. In practice, you know that transition from a non-zero slope to a 0 slope will not be as abrupt. Okay. There will be a gentle transition from something where the slope is what you want to something where the slope is much smaller. Okay. So, we will have to figure out, we will have to come up with a clean acceptable definition of what it means to have a linear range. For example, one might say, okay, one thing for sure is that as I go on increasing the amplitude, the amount of distortion will go on increasing, isn't it? Okay. So, even if the I versus V characteristic is not a nice piecewise linear characteristic like this, but some kind of gentle curve, as I go on increasing the input amplitude, the levels of harmonics in the output current must go on increasing. So, one might say, okay, I define my linear range as that voltage which gives me say 1% harmonic distortion in the current. Okay. So, we keep that as a standard definition and keep going ahead. So, this way we are all talking about the same thing when we say the linear range of this I to V V to I converter is so many millivolts, so many volts. Okay. So, that is just a matter of notation, but all that I am emphasizing at this point is that every transconductor, depending on the way it is designed, is associated with a linear range, and if you want your filter not to screw things up, you want to make sure that the input to the transconductor is never exceeds the linear range. Alright. So, if now every transconductor has got a linear range, it must follow that if I build a network with many such transconductors, that resulting network will also have a range of amplitudes beyond which something bad happens somewhere inside, and therefore the output is distorted. You understand? So, in other words, every filter built using transconductors, all right, has a permissible maximum signal level beyond which the output is severely distorted. Does it make sense? Okay. Now, the linear range of the filter should not be confused with the linear range of the transconductor. All that we say is the linear range of the filter must in some fashion be related to the linear range of the transconductors, but need not be the same. Okay, it could be more, it could be less. Why do I say it could be more? Is it possible that it can be more? I mean, one simple trick to take is, okay, I will say, okay, my filter can handle 2 million volts, then put an attenuator with a ratio of 1 by 2 to the 8, and then all the signals internally become very small, and then my transconductors are able to handle it, and so on. So all that you can say is that the linear range of the transconductors is in some fashion related to the linear range of the filter, but both need not be necessarily the same. So and though I just talk about transconductors here, this holds for filters built using active elements in general, because we know that every active element, be it a bipolar transistor, a MOS transistor, whatever transistor you have, has only a range of bias conditions over which the transistor behaves like a incremental voltage controlled current source. Okay. The moment signals exceed either these quiescent conditions, the transistor does not behave like what you want, which means that the behavior of the entire circuit gets affected, and so on. So every active filter is associated with a maximum signal level. Okay. And as we will see going forward, this maximum signal level is related to the power supply voltage. Okay. Okay. All right. Now, please note that this is in contrast to a passive filter, where inductors and capacitors were only used. They are fundamentally linear elements. So in principle, you would be able to put as large a signal as you want, and since these elements are fundamentally linear, you would be able to get this filtering action without any distortion for very, very large signals. But that is not the case in an active implementation, simply because every transconductor you build has a finite linear range. So this prevents signals from becoming extremely large, or therefore puts a maximum limit on the maximum signal level that the filter can handle. Okay. Now, at the other end of the spectrum, it turns out every active device and resistors, okay, add noise. We will get into a more thorough discussion on noise going forward, but at this point all I wanted to understand is that there is now every transconductor here, for example, ideally you would expect what would you expect this current to be ideally? GM4 into Vi. It so turns out that the moment, you need to put transistors in various configurations to cook up GM4. It turns out that in that process there is also, apart from pushing out GM4 times Vi, it also pushes out a noise current, alright, and similarly GM2 also pushes out a noise current, GM1 adds a noise current, GM3 adds a noise current. Now, if all the transconductors are adding noise, then it therefore follows that the output signal here will consist of what? Not only will it consist of Vi being filtered by the filter transfer function that you intended to realize, okay, it also consists of noise, because this node is influenced by the potential at, so this node is influenced by the potential here, and this node in turn is potential is influenced by the potential at this node. So, and this node is basically, you can see that it not only consists of signal current but also noise currents from all these transconductors. Now, if the input signal is very, very small, what do you think the output signal here will consist of? Without getting into the details of how that noise might look like, one thing that's apparent is that given that there are so many noise sources in the network, the output voltage will consist of the input component plus some noise component. Now, if the input becomes smaller and smaller and smaller in magnitude, then what will occur at the output will largely be noise. Okay, and this is, mind you, this is not noise from the input. This is noise that the filter has generated internally. You understand? So, in other words, the filter output is noisy, all right, and if Vi is too small, the output is largely internal noise generated by the filter. Does it make sense? Okay. So, if you look at, if I plot the signal to noise ratio, okay, as a function of input amplitude, okay, what would you normally think if the input amplitude, let me plot the input amplitude in dB normalized to, I mean, you can never plot an absolute quantity in dB. dB is always, it's a logarithm of something. You can't take log of a number. It must be, I mean, of something with dimensions. It must be normalized to something. I just chosen that normalized quantity to 1 volt, so that A in dB simply means, what I mean is 20 log A by 1 volt. Similarly, the SNR can also be plotted in dB, which is defined as 10 times log of P signal divided by P noise, where P signal is the power at the, I mean, let's say I put a sinusoidal input tone, right? At the output there will be some sinusoid plus some noise. I will find the power of the sinusoid and the power of the noise, take 10 times log of P sinusoid by P noise. Going forward, I mean, I realize that several of you, how many of you have not seen or made any noise calculations before? I mean, I would think the BTechs who took EC201 last time, you are aware of noise, or you don't know if you are aware or you are not aware? So, you are able to, you understand what spectral density is and all this other stuff. Yes? Not so much. Okay. Okay, so in any case, I plan to cover this in reasonable level so that you'll be able to do something useful with it. So anyway, so we'll figure out how to compute P noise and all that stuff later, but at this point, yeah, at least intuitively, you know that noise has got, that waveform has got some power. I'll measure the signal power by noise power and take 10 log, and that gives me a number in dB as the signal to noise ratio at the output of the filter. Okay. Now, if all the transconductors were perfectly linear, right, in other words, the linear range was infinite, if I increase the input amplitude by 1 dB, right, what do you think will happen to the SNR? It should also, yes, so if I plot the input amplitude in dB versus SNR in dB, what will I get? I'll get a straight line, and what would be the slope of that straight line? 1. This is provided the linear range of all the transconductors is infinite. Okay. Now, obviously, all the transconductors have finite linear range. So, if I go on increasing the input amplitude, what will eventually happen? You will find that some transconductor or a multiple of them inside the network will get out of their linear regions of operation, thereby adding distortion. Okay. Now, if we treat noise and distortion as within quotes garbage which you don't need, and plot when we say SNR, we basically are plotting signal, power of the signal to power of everything, the output minus signal. In other words, power of signal by power of everything else. You understand? So, if I go on increasing the input amplitude, what will happen eventually to the SNR? It will start dropping simply because the distortion starts to increase. So, it will do this, and beyond a certain point it will just drop. Okay. Drop due to distortion. In other words, we already know that the filter can only handle a certain given signal level, it cannot handle arbitrarily large signal levels. Okay. Now, as the input signal becomes very, very small, what do you think will happen to the SNR? What will happen? This will go on going down to minus infinity, right? If you plot the log of, as the input amplitude becomes smaller and smaller, the SNR becomes smaller and smaller, which means the log of the SNR becomes closer and closer to minus infinity, right? So, obviously, if the SNR becomes too small, in other words, the ratio of the signal power to the noise power is very, 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 very small, then obviously you cannot make any sense out of what is coming out of the filter, because what you are just looking at is noise. Okay. All right. Now, therefore, one needs to kind of define, to be able to define what the lowest level of signal that's permissible into a filter, one needs to define what one needs, what one means when he says, this SNR is adequate, or rather the output of the filter is intelligible to me, I can make sense of what is coming out, and we need to define that thing, correct? And that definition is arbitrarily chosen to be 0 dB. In effect, what you are saying is that even if the ratio of the signal power to the noise power is 1, okay, I am able to use that information, correct, and make some sense out of what is coming. Okay. So, and as I said, this choice of 0 dB is quite arbitrary and is just a standard choice, and everybody just follows this as convention. All right. Now, therefore, there is a minimum level of signal below which the output of the filter just makes no sense. right. All right, and there is also A max all in dB. Okay. So, we see therefore that an active filter has a very definite range of signals that it can handle, right. If the input signals are too small, then you can't make any sense of the output of the filter simply because the output signal is being dominated by noise generated internally within the filter. On the other hand, if the input signal becomes very, very large, then you still cannot make any sense at the signal at the output of the filter simply because the signal is so large that some transconductors inside have gone into their nonlinear regions of operation, thereby adding significant harmonic distortion, and therefore which is also not desirable, and therefore the output is largely useless. Okay. So, this range of signals over which the filter does a decent job of filtering the input while the output still is intelligible is called the dynamic range of the filter, right. So, dynamic range is A max by A min, or dynamic range in dB is A max in dB minus A min in dB, right. This A max is coming due to distortion, this A min is coming due to noise. You understand? All right. Now, the question is, yes. So, I have this filter. So, some Vi, it's got transconductors and capacitors. Okay. I have not put in resistors simply because I know that any resistor can be realized by taking a transconductor and connecting its output to the input in the proper sign. Okay. So, and this is some output. Okay. All right. So, now let us say this filter has got some dynamic range dr1. All right. Now, if I took another identical filter, in other words, I copy and paste what will be the dynamic range of this filter F2? This dynamic range will be dr. Okay. Now, let us say, finally, capacitors and transistors and all this, these elements, when you make them on an IC, they occupy some area, correct? Let us call that A1. And clearly, when you implement these transconductors, they will draw some current from the supplies. We already agreed that these transconductors can't be floating, they must be drawing power from the supply, and therefore, the power dissipation is P1. Okay. So, clearly, since F2 is simply a copy and paste version of F1, the area and power will be the same, correct. Now, what do you think will happen if I join the corresponding nodes in these two filters? Okay, what will be the current flowing through these wires? So, in other words, I join these two filters to make a composite filter. Okay. All right. In other words, both these filters are excited with the same input voltage. Since F2 is a copy and paste version of F1, the potential at a node N1 here will be exactly the same as the potential at node N2 in F2, correct? Which means that if I join these two nodes with a wire, what do you think will happen? No current will pass through the wire. So similarly, if I join this output like this and this output like this, okay, no current will flow through any of these wires. Okay, that is assuming no noise, right? All right. So what is happening to the area now of the composite filter? In other words, if I denote two of these guys being driven by the same input, and if I join all the corresponding nodes in F1 with those in F2, no current will ever flow through any of those wires because both the potentials are the same. Okay. Now, can you please turn off your phones? F1 and F2 are connected in parallel. What can you say about the area? Area is 2A1. What about the power? 2P1. Okay. What can you say about A max? A max, what is A max? Is the A max, let me remind you, is the maximum amplitude you can put into the filter F1 or F2 before the output starts to become distorted. So if clearly F1 and F2 have the same A max, if I now put F1 in parallel with F2, where meaning of parallel is in this sense, then what comment can you make about A max of the composite filter? Somebody says it will be double. Same. Why is it the same? Yes, please note that in fact it does not matter if F1 and F2 are linear networks or non-linear networks, as long as both of them are exactly identical and both are being driven by exactly the same input, then the corresponding node in F1 will always have exactly the same potential as the corresponding node in F2. So if I have a wire between those two corresponding nodes, no current will ever flow through them, right? So if F1 starts to distort, F2 will also start to distort, right? And when I join them, when I connect them in this composite fashion, the composite one will also start to distort at the same signal level. Is that clear? In other words, when I connect F1 and F2 in parallel, A max remains the same. Is that clear? All right. Now, what can you say about, what is the interest in doing all these calculations? We'd like to figure out if I took two identical things and put them in parallel, what happens to the dynamic range. To find the dynamic range, I need to find the maximum signal level and the minimum signal level. So, if I assume that A max and A min are the maximum and minimum signal levels that filter F1 can handle. Okay. In other words, DR1 is A max by A min. The question obviously now will be, hey, if I put these two together in parallel, we know one thing. We know that the A max doesn't change. What can you say about the frequency response of the composite filter? It remains exactly the same. So, in other words, if I took two identical filters and put them in parallel, the frequency response remains identical, or it doesn't change. So, the response is the same. The composite filter occupies twice the area, right? It occupies and consumes twice the power. The maximum signal level is unchanged and remains A max, right? So, we would like to see what happens to the minimal signal level. I mean, clearly if the minimum signal level also remains the same, what do you think will happen? The dynamic range remains the same. So, do you think that's something that can happen or cannot happen? No. No point in doing this. Okay. So, yes. There is no point in doing this, but there is a point in doing the opposite, which is I can think of any filter as the parallel combination of two identical halves, isn't it? Correct? And each half will occupy half the power of the entire filter. So, if the dynamic range didn't change, right, then I will take the filter, cut it, chop it in half, and I have half the power, same dynamic range, half the area, right? And then I will say, hey, I can do this once more and once more and once more and once more, right? So, I will eventually have a filter which doesn't occupy any space and doesn't consume any power at all and has the same dynamic range. So, you understand? So, clearly this sounds too good to be true, and as you probably learnt, or if you not, you learn it the hard way, that anything that sounds too good to be true is probably too good to be true. So, that can't happen. So, whether you know how to calculate dynamic range or not, one thing you must know is that it probably cannot remain the same. If my answer says it remains the same, then I know that I am making a serious mistake somewhere. You understand? Okay. Now, given this background information, let us go and actually calculate the dynamic range. So, if I, in other words, to find A min, what do I have to do? So, in other words, all that I have to do is find the noise power at the output of filter 1. By definition, A min is that input voltage amplitude where the power of the signal is the same as the noise power. In other words, if I find the noise power coming out of the filter, then from that I can go and calculate A min. Does that make sense? So, alright. So, in other words, to calculate A min, all that I need to do is to find the noise power at the output of the filter, right. For that I need to set the input to 0 and okay. Alright, and I will measure, because the devices are noisy, between these two nodes. If I say place a voltmeter or something, it will keep registering some random voltage, okay, from which I can go and find the noise power. In other words, as far as these two nodes are concerned, I can form a Thevenin equivalent, correct, where there is some noise source and some impedance Z. Does it make sense? For those of you who are not very familiar with noise calculations, an easy way of understanding this is to assume that all these noise sources are not really random sources but some deterministic sources. So if you have a network with a whole bunch of sources inside, if I am only interested in the behavior at a terminal pair, then I can reduce the entire network to either the Thevenin equivalent, which consists of one voltage source and a Thevenin impedance, or to a Norton equivalent, which consists of one current source in shunt with a admittance, right. So here I have chosen the Thevenin equivalent. Okay, I mean, and it goes without saying that this source noise, this so-called noise source, is got to be a function of the topology of the network inside and the strengths of various noise sources inside the network, correct? All right. Now clearly if I copy, let me call this Vn1, okay. Now, so clearly the to find A min, what will I do? To find A min, all that I need to do is find the mean square value of this noise source. I mean, if I just put a voltmeter at the output of the filter, and I'll obviously, what I see will be Vn1. I want to find its power, so I will just average Vn1 square. Does it make sense? Okay. And now I will equate this to what is A min? If I find Vn1 square equal to A min square by 2, since A min is a sinusoid and A min square by 2 is the power of the sinusoid. Clear? Okay. Now, since F2 is a copy and paste version of F1, it follows that the A min of F2 will obviously be the same as the A min of F1. Now we are interested in what will happen when I parallel F1 and F2. So if I connect, so if I copy and paste this, okay, this is F2. Now I'm going to connect these two together, which means in the Thevenin equivalent what must happen? In the Thevenin equivalent, all that I need to do is connect this guy to this and this guy to, and this is my composite output, correct? All right. Now we already know that mean square value of Vn1 is A min square by 2. Mean square value of Vn2 square is also A min square by 2, right? Okay. Please note that even though these are two identical filter networks, the noise waveforms injected by various transistors inside F1 and inside F2, while they have the same statistical properties, the absolute waveform will not be the same. You understand? Okay. Just like if I divided this class into 2 and gave you a test, it's very likely that the average here and the average in the other half, if I chose the order randomly, will be the same. The standard deviation will also be the same, but that doesn't mean that for every person getting 6.5 on 10 here, I will be able to find another person in the other half also getting the same marks. You understand? Statistically, the two halves are equivalent. Doesn't mean that the two of them are exactly the same. In the same way, Vn1 and Vn2 are statistically equivalent. but do not have the same absolute waveform. So, what is the output? If I now join these two filters together in this fashion and put a voltmeter across the two in parallel, what voltage will I measure in terms of Vn1 and Vn2? No, please look carefully. Alright, so it's basically, if you don't like it that way, I will. This is F1. This is F2. This is Vn1, Z, Z, Vn2. So this voltage therefore must be Vn1 plus Vn2 by 2. Correct? So the mean square value, so to find A min, what should I do? What am I supposed to do now? I want to find the mean square value of Vn1 plus Vn2 by 2 whole square, right? And this must be Vn1 square by 2 plus Vn2 square by 2 by 4, I am sorry. Plus 1/2 of Vn1, Vn2, the average value of that. Okay. So Vn1 and Vn2 are statistically equivalent, but one waveform is completely uncorrelated with the other because they are happening in completely different circuits. Correct? Which means, what is the average value of Vn1 times Vn2? The average value of Vn1 times Vn2 must be 0, which means the mean square value at the output of F1 parallel F2 is Vn1 square by 4 plus Vn2 square by 4, which is nothing but A min square by 2 times 1/4 plus 1/4 times A min square by 2, which is 1/2 A min square by 2. Okay. So what has happened to A min now of the composite filter? Has been reduced by a factor of √2. So the composite filter here A max is the same, A min has gone down by √2. Does it make sense?
So why is it brought in
Vn1 and Vn2 are completely independent, right? And because they are happening in two different networks. So if I multiply them and have, it's more also important to note that Vn1 and Vn2 are zero mean. Okay, if they are not zero mean, then again, I just give up this job and go and build a filter and then tap that energy and supply it to the grid, right? And then we'd all be very happy. You understand? So all these are zero mean processes, okay, and uncorrelated with each other. So when you multiply them and average them, the result must be 0. So we see that the maximum amplitude is the same. This everybody understands. The minimum amplitude when I parallel these two filters has gone down by a factor of √2. Therefore, the dynamic range has increased, has gone up by √2. In dB, how much is this? It's 10 log or 20 log, I'm sorry. Which is 10 log 2, which is 3 dB. You understand? So 3 dB may sound like a small number, right? Okay. But you see that to get 3 dB increase in dynamic range, what does it cost? It costs twice the area and twice the power, right? So what I wanted to bring to your attention was the fact that 3 dB in dynamic range is not something to be sneered at, right? So somebody says my power is my dynamic range is 65 dB, and one guy says my dynamic range is 68 dB. You might say in 65 dB, 3 dB, what's the big deal, right? The big deal is 2x in area and 2x in power. You understand? So 3 dB is serious business. All right, and this also gives you a way in which you can compare different filter designs. Some of these filter designs, it's very likely that all filters that have ever been designed are all targeted to the same dynamic range. In some applications, for example, a 40 dB dynamic range may be sufficient, right? In several other systems, a dynamic range of 90 dB is perhaps what you need, right? So in order to be able to cover, so you can never expect a filter with a dynamic range of 90 dB to be consuming lot less power than the same filter transfer function designed for 40 dB dynamic range. Okay, but in order to be able to compare the quality of these designs, you need to account for the difference in dynamic range and so on. Yeah. I am now talking about two identical filters. Yeah. So the question he brought up is okay. So obviously you're putting in a sinusoidal tone. So are you putting the sinusoidal tone at a frequency well within the passband of the filter, or are you putting it in the stop band? The generally accepted thing is to put, obviously it doesn't make sense to put anything in the stop band because nothing is coming out of the filter. So the question is, where in the passband do you put it, right? And it turns out that a common good place to put it is somewhere where at passband edge by 3. Okay, that's a good rule of thumb. I'll tell you why this is a good rule of thumb when we get there, right? So the in-band tone, the tone must be in band and roughly about band edge by 3. Okay, so that is this discussion. Okay, so in general, if I put these two filters in parallel, I am getting a 3 dB improvement in dynamic range. So which means that this node is getting connected to this node is getting connected to this node is getting connected to this node, and so on. So in other words, wherever you had one transconductor in the original network, when you put two identical filters in parallel, it means that every transconductance has become twice its value. What about every capacitance? Every capacitance has become twice its value. In general, every conductance and capacitance, or every admittance, has become twice its value. In other words, every impedance has become 1/2 its value. So if you scale, what do you call a network where every impedance is 1/2 of that in some other network? It is nothing but taking a network and scaling its impedance by half. You understand? So impedance scaling by a factor of n results in a dynamic range increase by how much? Okay, so impedance scaling by 1 by 2, that is, in other words, you take the network and reduce every impedance by a factor of 2, right? Dynamic range goes up by 3 dB, and how do you get this 3 dB? It's 20 log root 2. So impedance scaling by 1 by n, the dynamic range must increase by 20 log root n, which is 10 log n dB. Does it make sense? Okay, and please note this is a fundamental trade-off. You have not really assumed anything about technology, MOS transistors, bipolar transistors, anything. Okay, all right. Okay, now